In the previous video, we looked at how the chain rule applied to the scenario where z was a function of two variables, and each of those intermediate variables was a function of a single variable. In this video, we're going to start by looking at case 2, which is going to feature a function z as a function of two variables again, but each of these intermediate variables are going to be functions of two variables themselves. So u is going to be a function g of xy, and v is going to be a function h of variables x and y. One thing to be careful about in this kind of a setting is that we do need u and v to be functions of the same two variables. So if u was a function of x and y and v was a function of s and t, then the chain rule as we're about to describe it would not apply because they're variables of different types of or different variables. So it is important that u and v have the same independent variables as each other. Right? And so in this case, if we sort of do the chain, the tree diagram that we did before, all right, we're going to start with our dependent variable z. We're going to have our intermediate variables u and v. And then underneath each of these, we're going to have an x and a y. Right, so there's different ways you can draw this. I'm going to draw a separate x and y for each of those variables, although it's certainly possible to draw just one x and one y and then have arrows cross, but that's a little bit sloppy to do that. And we're going to draw arrows from every variable, each of these variables down to the variables below it. And then we label everything appropriately. So this is del z, del v on the right side, del v, del x, and del v, del y. And on the left side, we have del z, del u, del u, del x, and del u, del y. So when we go to write the chain rule, right, the chain rule we're going to compute, in this case we have to compute two different derivatives. There's going to be two partials to compute. We're going to be able to compute del z, del x, and del z, del y. Right? And so for del z, del x, what we want to do is look at every possible path from z down to x. And so here's one, and here's another. Right? And those are the only two ways we can go from z on the top of the diagram down to x. And so along each path, we're going to multiply the derivatives that appear and then add them together. So del z, del x from this picture will be del z, del v. I'm sorry, del z, del u multiplied by del u, del x. That's the path on the left. The path on the right is del z, del v multiplied by del v, del x. And so there is our chain rule in this for this particular partial. Notice that all the derivatives in this equation are partial derivatives because every function in this scenario is a function of multiple variables. Right? For del z, del y, we need to go from z down to y. And so we find a path. There's one there. And there's another over here. And so we'll have del z, del u multiplied by del u, del y plus del z, del v multiplied by del v, del y. So you'll notice that these two equations are exactly the same, except for in the first one we have a del x in three places, and in the second we have del y. And this is fairly typical. We're just looking at the variable that we're differentiating with respect to, and typically this will be symmetric in the variables. So let's take a look at an example. So let's say z is the function e raised to the u plus 2v power. U is the function x cubed y. And v is the function y squared minus x. Okay. And so we want to find both of the first order partials of z with respect to x and with respect to y. All right, so we have our chain rule. All right, we know del z del x is going to be del z del u multiplied by del u del x, and adding to that del z del v multiplied by del v del x. So we just have to compute these four quantities. So differentiating z with respect to u, we're just going to get e to the u plus 2v. We would multiply by the derivative of u plus tv with respect to u, but that's just 1. So we're going to have e to the u plus 2v multiplied by del u del x, so that'll be 3x squared y. We're going to add to that del z del v. So this will be 2 times e to the u plus 2v. So the derivative of u plus 2v is 2 when we differentiate with respect to v, multiplied by del v del x, which is just -1. Right? So in this case, we have this particular form, and this would actually be, good enough, to some degree. What we would really need, if we wanted to simplify it, we could do that. But then we could just replace u and v with the expressions in terms of x and y. But often, because that will be difficult to do, oftentimes we will leave the final answer in terms of our intermediate variables as well, knowing that in order to actually evaluate this, we'd either need to figure out the values of u and v or substitute the values of x and y in for u and v. But in this particular case, we've applied the chain rule and we have a derivative that we can use. So we're going to leave it in terms of both the intermediate and independent variables. Right, to compute del z del y, we follow a very, very similar pattern. So we start with the chain rule, del z del u times del u del y plus del z del v multiplied by del v del y. Right? And del z del u is exactly what it was before, e to the u plus 2v multiplied by du dy now is just x cubed. Del z del v is, again, 2e to the u plus 2v. And del v del y will be 2y. Right? And again, if desired, you could simplify this a little bit. You could factor out the e to the u plus 2v and then substitute in the values for u and v if you'd like. But for this kind of a problem at this stage, I'm just going to say this is good enough. Again, we can always do those little things, but the big point here is to find a usable derivative, and in any kind of useful setting, if we wanted the value of del z del y at a particular point, we could compute it with this. We could find x and y. That would allow us to find u and v, and then we could substitute all of those values into this particular derivative and be able to use this in that way. All right, so now that we've seen a couple different cases of the chain rule, it's time to just state a general case for the chain rule that will apply to any situation. Right? But sometimes looking at these specific cases will help sort of visualize what we're going to be doing in the general cases. All right, so this is what I'll just call this the general version. It will include the two versions we've already encountered and also cover any other situation you might encounter in the future. So what we're going to do for this particular version is we're going to suppose I have a function z, which is a function of n variables. So I'm going to call it u1, u2, up to u sub n. So it's a function of n variables. We've been looking at the case where n is 2 in our scenarios, but we could have 3 or 4 or 17, however many variables. And we want to suppose this is a differentiable function. So this function f is differentiable with respect to each of those variables, u1 through un. Right? And in addition to that being differentiable, we want each of the u's, so I'm just going to say ui to represent one of the arbitrary variables u. We want each of the u's to be a function, say g sub I, of variables x1 through xm. We want that to be differentiable with respect to x1 through xm. All right, so this is our setup. We have a function. We have z as a function of n variables, and it's a differentiable function, and each of those variables is a function of m other variables. And again, those are all differentiable with respect to those variables. So we have just a very general case, bunch of functions, each function is a function of some number of variables. And in this context, the chain rule tells us the following. So it says that if I want to differentiate z with respect to one of the x's, so say del z, del xi, then we're going to take del z, del u1, multiplied by del u1, del xi. Right, so z differentiating with respect to u1, the first variable, multiplied by the first variable differentiated with respect to the variable that we want, plus del z, del u2, multiplied by del u2, del xi. And we're going to have one of these summands for each variable u. So there'll be n of these summands. The last one will be del z, del un, times del un, del xi. And so this tells us how to compute this derivative with respect to this variable. But the nice thing about this is that we really don't need to memorize this particular rule with its notation and all of its generality. In particular cases, when this comes up, when we have functions that don't fit the two cases that we've looked at already, what we should always start with is make a tree diagram. And the tree diagram will give us this rule every single time. So let's look at an example of the general chain rule and how we can apply it. So let's say that we had a function w. So it'll be 2x y cubed plus x squared z minus yz squared. So this is our function w. Notice that it is a function of three variables. And then I'm going to write each of my three variables x, y, and z in terms of two variables s and t. So I'm going to say that x is given by s minus t, y is going to be given by s squared plus t squared, and z is going to be given by s times t. Right, so I have w as a function of three variables, and each of those variables are functions of two variables. And so what we want to do here is we want to find w sub s and w sub t. Right? So these are just the notation for partial derivatives of w with respect to s and t, respectively. And we are going to allow here, I'm going to be very specific, we're going to allow it to be in terms of the intermediate variables and the independent variables. All right, so we're not going to have to do that final step of substituting the functions of x, y, and z in terms of s and t back into our equation. If we had to do, we could. It's just going to be very ugly, which you'll see when we get there. But the first thing we should do here to make sure we do the chain rule properly is to come up with a tree diagram and use that. All right, so our dependent variable in our case is w, so we'll start that at the top of the tree. We have three intermediate variables, x, y, and z. And each of those are in terms of two independent variables, s and t. So like we did before, I'm going to write those variables under each of our intermediate variables. Okay, so I draw all the arrows from the variables in one level to all the variables below it. Okay, and so when we write down the chain rule, for example, when we want to find w sub s, the partial of w with respect to s, we're going to look at all the different ways we can get s, go from w at the top to s at the bottom. Right, so on the left side here, right, we can do this. And so this is, we're going to take the partial of w with respect to x multiplied by the partial of x with respect to s. We're going to then look at in the middle, and we can see that we can get there along this path. So that's del w del y del s. And the third way we can get to down to s is going through z. So that's del w del z del s. Right, now you can probably see once you get comfortable with the chain rule, the tree diagram is not 100% necessary every time. You can sort of see the pattern. It's going to be differentiating w in terms of all of the intermediate variables, and then all the intermediate variables with respect to the variable that you want, in this case s. But the tree diagram is a good way when there's a lot of variables to make sure that you organize everything properly. All right, so now we just have to compute these 6 derivatives. All right, so del w del x is going to be 2y cubed plus 2xz. Del x del s is just 1. Del w del y is going to be 6xy squared minus z squared. Del y del s will be 2s. And del w del z is going to be x squared minus 2yz, and del z del s will be t. Right? And so in this particular case, since we said we could leave this in terms of the intermediate and independent variables, everything here is an x, y, z, or an s or t, and so we can leave everything in this form. If you wanted everything in terms of the independent variable, then you'd probably want to simplify all this out, and replace the x, y, and z with the functions s minus t, s squared plus t squared, and st, respectively. But this is really just an algebraic mess, and so usually it's okay to leave things like this in these particular terms. So the second part here, w sub t, we're going to follow a similar pattern. So we know the chain rule in this case. We can either we can do the tree diagram if you want, but I'm going to skip that step in this case. It's going to be the exact same as ws, except for when we have differentiate x, y, and z with respect to s, we're going to differentiate them instead in terms of t. Right? And so the nice thing about this is that we've already computed 3 of these derivatives that we need. All the derivatives of w are the same. So we're going to get 2y cubed plus 2xz multiplied by dx dt, which would be -1. We'll have 6xy squared minus z squared multiplied by del y del t, which is 2t. And x squared minus 2yz multiplied by del z del t, which is s. Right, and so we can sort of just replace these 3 derivatives in terms of s with the appropriate derivatives in terms of t. And it makes computing the second partial a lot quicker.